Antoinette Stevens. I am a cybersecurity analyst at Principal Financial Group in Des Moines, Iowa, and I am the founder and executive director for Reboot Iowa, a nonprofit I founded to help adults learn tech literacy, basic coding skills, and then basic personal security practices. I am a member of the Des Moines City Sec DSM, and I'm an organizer for B-Sides Iowa, and I also help design CTF challenges for them from time to time. And then I also work at a arcade bar called Up Down, where I work on games, which is a new venture for me. I'm not really a hardware person, but I'm learning to be. Alright, so a quick disclaimer about learning styles. The title of this talk mentions the word kinesthetic, which is a reference to a learning style introduced in the early 90s by Fleming and Mills in the VARC questionnaire. So learning styles are traditionally researched and used to help teachers learn how to help their students learn better. But recent research has actually pointed out that learning styles are a myth. You don't actually learn better based on auditory or visual or anything like that. It's more of a holistic approach, which is really fun to find out when you're researching for a talk that mentions a kinesthetic learning style. But basically it's bullshit. So for the purposes of this talk, we'll just be going with the colloquial meaning, which is just hands-on. So it's just a hands-on approach to learning encryption. Alright, so I really wanted to learn encryption, but my job doesn't require me to know it or implement it in any way. I'm not a developer. And I also really like doing capture the flag competitions, and also never really knew how to do the encryption challenges, so it really helped me to combine the two together and learn encryption through CTFs and specifically through recreating them. So I decided to start looking up old CTF challenges, specifically their write-ups, and the two that I chose to kind of recreate was the AES ECB Mode challenges and the RSA short keyline challenge. And I kind of got my methodology down to 3 steps, which is to scope, research, and recreate. So I chose, scoping your challenge is really important, specifically because encryption is such a broad field. AES alone has several different modes and several different key lengths. And so scoping your challenge to something narrow helps you to learn in smaller, more digestible chunks instead of getting information overload by trying to learn everything at once and not really knowing where to start. So make sure if you're going to do this, you scope down to something very specific. And it'll also help you find challenges that are also going to be pretty specific. So research the challenge, which kind of speaks for itself, but you want to start reading about those concepts related to what you're looking at. So I looked a lot at why prime numbers are important for the RSA challenge, and I looked at what ECB mode even is while looking at that. You want to look up tools to help. While I was reading through these things, you come across tools, you kind of want to save those for later because they come in handy. And then most importantly, find write-ups that have similar challenges for the focus that you need. So I want to talk about write-ups specifically and what a good write-up is. So for anyone here who reads CTF write-ups, what do you think makes a good write-up? You can just shout it out. No one? Okay, cool.
I like seeing code examples.
You like seeing code examples? Anyone else? Okay. So for me, a good write-up provides details about the challenge itself. I know you can't see this. It's okay. It's not the point. But this is, there we go. This is a snippet from a write-up from Enigma 2017 called Broken Encryption. And it's kind of like a 007 challenge run. This program is running, you connect it to a server, it had this program that's like, enter your agent number, and then it spits out a bunch of jarbled text, which is your encrypted flag is in there. So he provided what was given to him as the challenge, which is really helpful when you want to build this later. You don't have to really do much guesswork. This code snippet comes from Seesaw 2017 and is called Baby Crypt. And so I think good write-ups have diagrams and really detailed explanations of the concepts in them. So this specific one is pointing out how ECB Mode encrypts data in 16-byte chunks. It mentions tools that are helpful, and you can't see it in here. So this came from an RSA article and mentions two tools, Yahoo and FactorDB, which for RSA short key length, as you'll see later, it's really important to be able to get factors from a part of your public key. So those two tools really help to make that process a lot quicker. And then they have detailed explanations of their solutions. So all of the write-ups that I chose to use to recreate my challenges included the scripts that were used to solve the challenge, and also a detailed explanation of why their scripts worked and why they chose to solve it in that way. So recreating the challenge, I started both by generating the keys necessary and making sure that I can encrypt and decrypt data before I went ahead and tried to break it. The AES challenge was actually the easier one to recreate. Simply the hardest part there was making sure I had the key correct, which is something that should have been a lot easier than it was, but it took a while. The RSA challenge is the one that gave me the most trouble, and I kept hitting 3 errors of note that I'll talk about in a moment. So the RSA short key length challenge, RSA stands for Rivest Shamir Adelman and is an asymmetric cryptographic algorithm, meaning it has a private key and a public key. So for the RSA challenge that I created, it wasn't actually based on a CTF, more so it was based on a write-up I found from Sebastian Neef on zeroday.org, where he kind of talks about why short key lengths in RSA are bad. So the 3 issues I ran into were A, generating the keys to begin with. A lot of things don't let you do short key lengths for RSA. Whether to pad or not pad the data that I was encrypting. And then finding the P and Q, which would help you get the 2 prime numbers you need to generate the private key. Alright, so this is a public and private key. It's fine, it's not used anywhere. Normally you don't want to share your private key with people. Usually you keep your private key and other people can have your public key to encrypt data, and you can decrypt it with the private key. So what you want to pay attention to here is the modulus and the private exponent. So the mod in the public key is what we'll use to get our P and Q, which can later go through another algorithm to get the private exponent. But I'll talk about that a little more in a second. Generating this was not easy, specifically because I originally tried to do it in Python, and Python won't let you generate RSA keys shorter than 1024 bits. So I wanted to do 256 bits, which meant I had to switch to OpenSSL. The next wall I kept hitting was whether or not I wanted to pad the data. So what we're looking at here is the PKCS1 padding scheme. And what it's basically saying is that you cannot encrypt more data than the size of your mod. So my mod is 33 bytes. And so the algorithm goes, the size of your data cannot be larger than 33 minus 11. So I can have 22 bytes of data and the rest gets padded, and then I can do encryption. Any more than that, and I'll get a lot of your data is too large errors, which is what I was dealing with before I decided to look at how padding works. If you don't want to deal with that, then you can do the raw flag in OpenSSL, and then you handle padding yourself. But 22 bytes is not a lot of data. It's barely a sentence. So it was really interesting trying to do this. It's just enough for a flag, though. And then once I was able to encrypt, the work began to get your P and Q from that modulus. So if it's fairly small for like 128-bit mods, it's pretty, or sorry, 128-bit keys, it's pretty easy to use a factor DB or even Wolfram Alpha to calculate the P and Q, which you just factor them. But for 256 bits, it took a lot longer, so I ended up downloading a program called MSieve. And so it took MSieve about 2 minutes to crack the P and Q. And you can go up to about 300 bits in an RSA key, and it'll only take a few minutes to crack. Any more than that, you start getting into the couple of hours, couple of days, couple of years range. And then once you have your P and Q, it's pretty easy to just Google around and run the extended Euclidean algorithm to calculate the modular inverse, which will give you the private exponent that you need to generate your private key. RSA is a bunch of math. Like, that's it. And it's not math that you need to know or know how to do by hand. It's just math where you need to know the different parts that go into it so you can plug it into something else someone else already wrote. So, AES 128, which is the key size, ECB Mode, which stands for Electronic Code Book, was actually pretty fun to try to figure out. So I began by replicating the 007 challenge that I had up before, and I used Python and used sockets and wrote a server to connect to, so that I can kind of copy the way that the original challenge worked. And it took longer than I'm proud to admit to generate the key simply because I didn't understand the structure of the key needed. But I ended up just doing an MD5, which had 128 bits in it, which is super simple. Although, a note, for actual implementations of AES, MD5 doesn't have enough entropy to work well. And, well, you're probably not doing AES 128 anyway. So, just a note. But once the key was properly generated, I could encrypt, and I knew I could encrypt and decrypt both ways. The trick with AES ECB is to make sure your blocks align. So like I said before, AES ECB mode specifically doesn't add any padding to the plain text before it encrypts it. So what goes in as plain text and comes out as ciphertext will always be that same ciphertext. So if you know part of the plain text in something, then you can see what the ciphertext looks like. So the trick with AES ECB mode is to manipulate your plain text and put in known plain text that's in the ciphertext and then look for matching blocks, which you'll see in a minute. What you need to know to do this challenge specifically would be the padding schema if there was one added. So this one added 1 and up to 14 zeros. And so since you knew kind of what the structure of the encrypted data coming out was, you could begin to guess your flag. So what you see here, the 2 red blocks, it's matching the pattern. So once you're able to align your 16 blocks, you can kind of begin to guess what the flag is by running through all of the alphabets and all of basically the full ASCII range to guess the flag. Which you don't have to do that by hand. There's a program out there already. Like I said, you can Google around and find scripts to do these things. But that's basically the challenge. And what this helped me understand is AES ECB mode is complete crap. Simply because it would be easy for someone to do that and guess what you're encrypting if they know how you padded it. And then if they know any of the plain text that might be in the ciphertext. So some of the lessons I learned while doing this: take good notes. It seems really trivial, but you'd be surprised how much you don't pay attention to what you're doing while you're doing it. It took me several hours to even relearn some things when I kept coming back to it. So taking good notes is super helpful, and also it helps to start bookmarking things as you go if you're not the type of person who likes to write things down. To Security via unsecurity. So this really helped me understand what is in place in certain popular programs to kind of protect developers by default. Like I said, Python doesn't allow you to generate keys less than 1024 bits. So the same goes for me learning that RSA isn't even used to encrypt full files. You usually encrypt something else and then encrypt the keys for that with RSA. So it was really good for me to kind of get that working knowledge, which if you ever read Stack Overflow, there are a lot of people in there who are more than willing to tell you how you're doing things wrong. Learn beyond the challenge. So like I said, you are scoping, which means you're focusing on a very niche concept, and that also means it won't translate to every situation. So just because you understand how to break RSA short key length doesn't mean you understand how to break other types of vulnerabilities in RSA. Doesn't mean you understand how to break AES CBC mode. So it really helps once you get the concept down and you're pretty comfortable with it to keep kind of building on that knowledge. So it's basically a don't stop here kind of thing. In the future, I'm really interested in learning more about the different modes of AES, and also there are a lot of different vulnerabilities with RSA. It's really easy to mess that up. So I'm really interested to learn about what else exists there. And then I really like doing this simply because my job doesn't let me code a lot, but I have a degree in computer science, so I like to do it from time to time. Not every day, I'm glad I'm not a developer, but I like that if I wanted to learn a new language, I have something that I can implement with it. That tends to be a blocker for a lot of people. You can go, I want to learn Ruby, but I don't have anything to build. So recreating CTF challenges gives you something to build. All right. Thank you. If you want to follow me on Twitter, it's Antoinette0x53, and I also have a website, AntoinetteStevens.com, where I do CTF write-ups. Sometimes I'll walk through write-ups CTFs that I've written, only after I know I won't use it again. And I also publish different talks that I give around the place. So if you're interested, thank you.